Our next speaker is not a former student, but has been teaching here and is sending many of our students to become industry experts as well. So Professor Umit Karabiyik is a professor in the Computer and Information Technology School here in the Purdue Polytechnic, but is also the director of the Ubiquitous and Mobile Investigation Techniques and Technology Lab. Umit, welcome.
We can set it up here. Lab is named after me. So yeah, I mean, within my lab, I had at that time, I think 9 graduate students. So we came up with this name. I'm very humble. All right. So I'm not going to ask if you can hear me because it's really better actually back there. It's better to hear than this front room. So my name is Umit Karabiyik. Thank you for the introduction. I'm Joel. So today I'm going to be talking about. So you might be scared a little bit because I'm an academic. I'm not going to go into the details of the research. Rather, I'm going to actually share the results of our research, and we believe it's going to be very useful for most of the folks here. So the talk is about the scalable and concurrent targeted research for digital forensics. So primarily, I'm working on digital forensics, cyber forensics domain. Mobile and IoT forensics is my specialty. And as an end product, usually what we do outside of, outcome of our research, we develop tools, techniques, systems for most of the time law enforcement, but also for intelligence agencies as well. So this is a acknowledgement from a funding agency. The project is funded by the AFRL and through the NextFlex. 4 years of research. It was a very long 5 stages research we did. And at the end, we developed a tool, and I'm going to be talking about this. So I just want to do another disclaimer. This tool is available under the government license to all the government agencies. If there are anybody here, please feel free to talk to us. And for the details, I have a graduate student here who has poster session, and we'll be talking about the more technical details if you're interested. So what is digital forensics? I know I have lots of students here. Some of you are familiar with this term, but there's always Merriam-Webster definition of forensics, right? But I also want to look at the Interpol definition because it's more applied. And that's what we are really actually using every day in our life as investigators or examiners in DFIR teams. So it's what we do. We apply computer science into legal problems, and that's in the law enforcement side. But we also deal with some other challenges in industry and corporates, and those challenges are dealt with some of the forensic techniques that we use. We technically do a lot of steps, but in this talk, I'll be specifically focusing on processing, analyzing, and reporting of digital evidence or traces of some actions in computing domain. So what's the problem? So, well, we all are aware in technology, there is a huge, massive amount of data. And like 15 years ago, I think the hype term was big data, but it never get better, right? It just gets worse and worse and worse. And in some disciplines, it actually got even worse, like digital forensics and incident response as well. So handling this, massive data is actually becoming a significant issue in forensic investigations or intelligence, investigations. So every device now became a data source, and that, massive data is being produced. Another problem, related to massive data is how that data is unstructured. I wish to say how that data is structured. That would be amazing for us, so we can actually analyze it, easily. So the bigger problem in this case, related to digital forensics, we deal with massive data, and there are, significantly, urgent need to handle this, massive data, among those all problems. So the question is how we can identify forensically relevant artifacts, important evidence, or evidentiary value data within that massive data. So it's no longer a, looking for a, needle in the haystack. It's really looking for needle in the needle stack. So which needle you really need to find. So that's a bigger problem because data is not structured. So when we look at these unstructured data volumes by year, those folks in industry, corpus, let me know if this is wrong, but this is just one, data I found online, that massive data with zettabytes is actually increasing significantly. But what that really means is actually when we look at the, comparison, according to some of the sources online that we can find, 80% of the data is unstructured. So what structured data is very, very little. Forensically, we really deal with some financial data is structured, in computing environments like, mobile, IoT, or computer devices, or even like, sometimes in network data, network dumps. The data in like databases are usually very well structured, but understanding the rest of the data, which is 80%, is significantly challenging. And if you look at the right-hand side, the unstructured data component, that's most likely what we are interested in, right? When we want to have some idea about the investigative content. So those are like, messages, social media content, communications, calls, and all those kinds of information. So then, so what's the problem with that unstructured data? The currently available tools or techniques, to do investigators or DFIR team, digital forensics and incident response teams, are not really, capable of handling this. That's how we end up with this problem. So simply NASIC, National Airspace Intelligence Center, they reach out to us like say, none of the technologies can handle this data. How are we going to analyze this data? So then, we did some research and we look at the, the currently available tools. Those are like usually single and monolithic systems. And those are like single machine tools. They just run on one machine. Yeah, there are some parallelizations are happening, but they all use majority of the tasks are being handled in a monolithic structure. So that means like the data is not really handled in parallel entirely. It's not a distributed system. So most of you might be familiar already, when we look at the distributed versus single machine, solutions, the four criteria really comes up to the surface. Scalability, processing data, big data capability, that's very important. And also we look at the forensics analysis speed. And when we look at them, certainly single, machine systems do not really handle data well. So when I say large data, depends on your expertise, depends on the data that you are dealing with. You might be thinking like, some of you might be thinking like 2 terabytes is large. Some of you might be thinking like 30 terabytes is large or zettabyte is large. But in forensic investigations, it becomes a nightmare when you have like above 2 terabytes of data. It becomes literally a nightmare. One, because the systems we use crash. They don't handle that data. I'm not talking about analytics. I'm talking about even processing the data. So when analytics come in play, it's a disaster. So then obviously we need a distributed system. We need to have a distributed system can handle the massive forensically, available data. So as a researcher, we came up with some research questions and we wanted to, go after with these. And clearly the first question was, can a distributed microservice architecture be designed and implemented in an efficient way to process and analyze the data? And eventually in the second one, that process and analyze data can be also, analytically, further processed. Can we use some analytical tools like machine learning? Of course, we are going to sugarcoat it, right? Using AI. We are going to definitely adapt AI and make it, better it's intelligible making the data that doesn't make sense, it's unstructured, making it more intelligible for the investigators. So they were the two questions we were after. So we proposed a solution. We created a solution. We call it Forest, Forensic Search Toolkit. Simple. So this system enables the investigators for various things. But what are the most important first steps? I'm going to be going into details a little bit. Those are the refining searches. So refining searches for the precise needs that the investigators were looking for during their investigations. And we call them digital forensic investigations, but once again, the goal for this tool was targeted specifically for the intelligence agency, but we also wanted to keep the forensic values like validation of data, verification of data, making sure the content, if it is altered, identify those altered content, and all of these also in mind. So this can be also used by the law enforcement for their criminal investigations. So it allows custom search parameters for the investigators' needs. And this is highly adaptable tool based on their needs. And it significantly reduces this response time. So that reduction, I'm going to show you some time. Once again, don't judge this tool based on your expertise, because again, speed might be differently evaluated between different disciplines. Forensically, this tool actually provides significant efficiency in response time. So certainly it can be used for digital forensic investigations and intelligence investigations. So basically the goal is really from the unstructured massive data, having a better understandable, intelligible data for forensic examiners or intelligence officers. So what did we use? We used various technologies in the background, of course, to develop this whole system. So we use microservices. That's the key point of this entire scalable system. That's how actually it becomes a scalable system. Instead of monolithic structure or concurrent programming, we use microservices, and we actually took advantage of this architecture, and that actually allowed us to improve the efficiency and how effectively the data could be analyzed significantly. So we use some other modules. We use Kafka, and we use Python, of course, for that. Base APIs developed in net. There's so many different technologies we use in the background. This actually shows you how heterogeneous the system is, and it can be even like more heterogeneous with different type of programming languages that can be all adapted based on the investigator's needs. And we use LLM for the system. We use Ollama framework for a specific purpose because this is an intelligence agency. The developer intelligence agency, they wanted the system to be air-gapped. That was one of the biggest challenges. So it has to be air-gapped system, no connection whatsoever to the internet or other networks other than their own network. So therefore, we deployed Ollama framework and a LLM models into that. And the Grafana, we use that for real-time analytics or real-time log analytics and the performance and health of the system so that we can check and see if there are something's happening, if any module fails, any microarchitecture doesn't work as they were supposed to work. So my apologies. I didn't expect the screen being so little here. So the content might be very teeny tiny. So we have 4 main modules for the entire system, and these are all decoupled modules. And once again, actually new modules can be also added to the system as the investigators needs, but they were the 4 modules highly needed by the agency needed this product. And Ghidra module, some of you might be familiar with. It's used for the reverse engineering purposes, right? So we want to make sure the system calls are identified, binary files are identified, and definitely for malware, for the search of malware or some other malicious content, we use Ghidra in the background. All these binaries are analyzed and tagged for the investigators' further analysis purposes. And we have content indexing module, which also getting insights about the binaries. This looks to specific content, and when it actually goes through the content, indexing happens in 2 ways. So most of the forensic tools performs indexing on human readable content. If the content is ASCII and printable character on the keyboard, those contents are gathered. But that's a big problem because not all the malwares are human readable. They're binaries, right? And the code could be actually in it should be in searchable form when the content is hex or non-ASCII form. So that's what this tool also brings as an additional capability to the arsenal of investigators, so that they can actually do searches in hex. And there is a hash lookup module, so good, bad, known files during the investigations, and also other hash calculations based on the investigators' lists. If they have their own lists when they do their investigations, they can load up their good known or bad known files list, so they can be all matched against the files indexed within the entire system. And there's an LLM module. LLM module helps us. Again, it's a air gap system. It only works within the network or within the machine. And it actually provides tags and summaries of files, not only human readable content or not only the text content like PDF files or document files, it also reads the source codes, because that's a very important aspect that they want to identify the behaviors of some of the codes. So the LLM actually goes through those files and summarizes the actions that those codes or in any language actually performs, how they behave. So this is very important because investigators not always have technical skills in every domain, right? And we don't expect that. So if they don't know certain programming languages, providing summary to them for those files that are found is actually crucial. So, and why we use microservice architecture? We simply, we want it, scalable. We can actually increase the microservices as much as we wanted. It's horizontally scaled, and that could actually reduce the number of or the time actually passes for the both processing and analysis and the further reporting. So it's a resilient system. If any microservice fails, the system continues working, and we can see those fails in the Grafana as a reporting agent. And it's flexible. Technology heterogeneity is extremely important because not everybody, and it actually also relates to faster deployment and also bug fixing. So there are so many different languages they can work together within the system, and it's highly adaptable, and new modules can be created. Because I have little time, I'm going to skip this. But basically, the entire workflow works in a way that there's a Kafka, it's a message handler. It actually keeps, so like a handler, it handles all the microservices in a way that when the case is loaded to the system, it actually processes, analyzes, and provides some insights to the investigators. It works with all the case workers. Case workers work caseworkers work in an order that Kafka sends them messages for whatever analytics is needed for the investigation. So we tested our system on a pretty good machine. This was the test machine we were working on for development as well. So these are some of the file sizes. So we tested it on a regular, let's say, computer machine. The idea, by the way, just going a little bit step back, the idea for unstructured data coming from NASIC was that they said, consider any type of data is coming. It could be satellite data, it could be network data, it could be phone data, it could be computer data, any type of data. So when you think about it, these numbers actually might differ, and their importance actually might differ. So 4.5 terabytes of network data could be massive, or that amount of data for a mobile phone, it's hundreds of phones. It's crazy. It's a really big data. So handling that data is actually essential, right? And you can see how much time actually it takes to complete the tasks. And according to the agency, they were pretty, good, timing. So we did, case workers. It actually shows how this microservices structure actually, speeds up. For a certain number of files, as we increase the case workers, the time to complete also linearly, decreases as we have more case workers. And this is certainly, we don't have a limit for case workers for the system. It is highly adaptable, and examiners can choose, based on the resources they have, as many, caseworkers they can assign to this system. So finally, what we have is the approximate matching. This is very important, feature that we wanted to have, because in investigations, we don't always have exact matching of the files. Like, we don't have a file that is, forensically valuable that is going to be perfectly match what we found. So approximate matching allows us that if the files are similar at some, sense, those are also marked as, relevant in the same files. I'm going to show you an example here. So how this approximate matching with the graph works. So we choose a case, and then we choose the graph for all the files. This is entire files in directory structures. We look at the file similarities, and it shows if the files are like, there's a file over there, it's 100% match with all those versions. This is from the GitHub. We wanted to show the percentage. It also calculates the the percentage of the similarity between the files. That gives a significant insight for investigators. And there's a global search. This is also great that multiple investigators can work on multiple cases. And if they are allowed with their priorities and they actually also access control mechanisms, they can search through entire cases that they have actually a priority or clearance to look at those cases. And this shows that if there are matches between the files, cross cases, it also shows if the files are found, forensically relevant files are found on the certain projects or cases, it shows those similarities between the cases. So yeah, I talk about air gap system and Ollama. We adapted Ollama framework and we pushed Dolphin V3 model into that. So this is just one example. It shows that there is a file and it shows the description from the AI. Of course, to reduce the hallucination for the AI, the better models can be adapted, and that's also a pretty flexible system that we can adapt or deploy any models that we needed. All right, so pretty much we bridge the gap for scalability for the forensic domain and incident response domain. Big data processing is no longer an issue with this tool. And this has been actually used for almost for 2 years within the intelligence agency. And we are hearing great news from them that they are actually using in their investigations. AI-driven automation helps significantly and reduces a lot of reading the content. They have to understand the file contents, and it's a secure air gap system. And that's all from me. Any questions?
Thank you, Umit.